Determine whether the equation is an identity, contradiction, or a conditional equation. When you work through your linear equations, linear meaning they have an x power of 1, you can use distributive property to remove any parentheses you need. And that's what we're going to do on this first example is we're going to distribute 9. 9 times x, 9x, minus 9 times 1, that's minus 9. The other side, because it is identical, it doesn't matter what value of x that you pick, that's always going to lead to a true statement, and that's called an identity. On the other end of the rainbow, when you solve a linear equation, and again, we're going to use distributive property, 9 times x is 9x, plus 9 times 1, that's plus 9. Now this time we don't have identical matches, but what we find is in order to keep this scale balanced out, we subtracted 9x's from both sides. That way you keep the equation balanced and you haven't done any illegal moves. 9x minus 9x is 0. We drag this 9 down. 9x minus 9x is 0, and we drag this 1 down. Since the variables totally fell out and we're left with contradicting numbers, this is a special case called a contradiction. And what that means is no matter what value of x that you choose, you can never get that statement to be equal. Solve each linear equation. Our first equation, we have 7x plus 4 equals 32. Think of your equal sign as the balancing point in a scale. If you add the same amount to both sides of a scale, it remains balanced. If you take off the exact same amount, both sides, it stays balanced. You can do that with numbers and variable terms. Just be careful to do them one at a time so that you don't overload yourself. For this one, we have 7x plus 4 equals 32. We only have one variable term, but we have two numerical terms. If I remove 4 from both sides, I've performed a legal move. What it also does is it separates my variable term from my numerical terms. 4 minus 4 is 0. 32 minus 4 is 28. Once you have separated your variable term from your numerical term, at the very end, your final step will be to divide by the number attached to x. If you divide both sides by 7, that will lead to 1x equals 4. In our other equation, 8 minus x equals 19, we have a variable term and two numerical terms. In class, you guys suggested we move the 8 over, and that's a good move. If we take 8 off of both sides of the equation or the scale, it remains balanced. That leaves us with 0 minus 1x equals 11. Negative 1 times x, we divide off the negative 1. Just remember, whatever's attached to your x, you divide it off. Divide both sides by negative 1, and that gives us 1x equals negative 11. Continuing with solving our equations, we have 2x plus 8 equals 10 minus 7x. In order to separate the variables from the numbers, we use adding or subtracting. You guys told me to use a subtract 8 as the first step, and that's totally fine. Subtracting 8 from both sides leaves us with 2x plus 0 equals 2 minus 7x. Now, add 7x to both sides of the equation. It keeps the scale balanced. 2x plus 7x is 9x equals 2. That goes to 0. And then 9's attached to x, so divide both sides by 9, and our answer is x equals 2/9. Our next equation, 5y plus 3 equals 8y minus 5 plus 4y. Again, think of the equation as the balance in a scale. These two terms are on the same side of the scale. So if I combine these into a 12y, I haven't tipped it at all. It's still a balanced scale. It's also one less term to have to worry about. We have two variable terms, two numerical terms. If you move the smaller of the two variable terms, it will keep your variable term positive. Subtracting 5y's from both sides maintains the balance. That leaves us with 3, 7y minus 5. Now we have a variable term on one side of the equation only. By adding 5, we get the numerical terms all on the other side. Adding 5, that gives us 8 equals 7y. That'll go to 0. Divide by the number attached to your variable. Dividing by 7 gives us 1y equals 8/7. Our final equation, solve 9x minus 12 equals 3x plus 2 times 3x minus 6. This 2 and 3x minus 6, those are multiplied together, distributing 2. The rest of the problem stays the same. So we have 9x minus 12 equals 3x. This 3x is not involved in the multiplication, only the positive 2. So that's 6x minus 12 when you distribute. Just like the previous example, these two terms are on the same side of the scale. So by just combining them, 9x, we haven't tipped it. These are both on the same side, and the total weight is 9x. This one's a little sneaky. Remember, when you run into identical sides, you have an identity. Any value of x that you pick will satisfy that statement. Now we're going to get into some equations that have fractions, and we want to eliminate the denominators. We have denominators of 2 and 4. We need to pick a number that's evenly divisible by both 2 and 4 if we want to eliminate the fractions. Numbers like 4, 8, 12, those are all good selections. In class, you guys told me 4. And so I multiplied both sides of the original equation by 4. 4 times 5x over 4 plus 4 times a half equals 4 times x minus 4 times 1/2. By picking a number that's evenly divisible by all your denominators, you get a nice clean cancellation. 4 goes into 4 once, times 5x is 5x. 2 goes into 4 twice, 2 times 1, that's 2. This term has no denominator to cancel, so it's 4 times x, or just 4x, minus 4 times a half. 2 goes into 4 twice. 2 times 1 is 2. And then to start separating variables and numbers, you guys suggested that we subtract 2 from both sides. That leaves us with 5x plus 0, nothing to write. Drop the 4x. Negative 2 minus 2 more is negative 4. And then to get the separation, subtracting 4 x's from both sides leaves us with 1x equals negative 4. In the next equation, we have fraction equals fraction. And that is a nice break to get when you're solving equations. If you've got fractions involved, but the original format is fraction equals fraction, then you can use a technique called cross multiplication. Multiply your diagonals together. 2 times 24x plus 3 equals, and then you multiply your other diagonals together. 1 times 7x plus 6. Distributing 2 times 24x plus 2 times 3, that's 48x plus 6, equals 1 times 7x plus 1 times 6. Separating variables from numbers, if you move the smaller amount of variables, your term will stay positive. Subtracting 7 x's from both sides leaves 41x plus 6 equals 6. And then to move your numbers to the opposite side, we're going to subtract 6 from both sides. 41x equals 0. Divide both sides by 41, and x equals 0. Okay. And our final example, we have an equation with fractions involved. Luckily, the denominator is the same. It's the variable x. So that makes it easy to choose your multiplier. Now, this one's not a candidate immediately for cross multiplication because we don't have fraction equals fraction, and that's okay. They don't always have to work out that way. But because I want to eliminate the fractions, I'm going to multiply both sides of the equation by x. So if you multiply the left side of the equation by x and the right side of the equation by x, you keep the scale balanced. X times 18 over x, your x's cancel. 1 times 18 is 18. Minus 8 times x, which is minus 8x. On the right side of the equation, x times 5 over x, your x's cancel. X divides into x once, times 5 is 5, plus 5 times x, that's plus 5x. Separating variables from numbers, in class you guys wanted me to move the negative 8x, which was a great choice because negative 8x is smaller than positive 5x. If you move the smaller amount, it will leave you with a positive variable term. So we have 18, this goes to 0, equals 5 plus 13x. And then now, to get the numbers on the other side, towards the top right of your screen, I just recopied the bottom here. I moved it up, recopied it. Subtract 5 from both sides. That keeps the scale balanced. 18 minus 5 is 13. 5 minus 5 is 0. 13x. Divide by the number attached to your variable. 13 divided by 13 is 1. These 13s cancel, makes a 1x.